All right, in this video, we're going to go and take a look how to write balanced equations for precipitation reactions and do a few extension problems that relate to that as well. And the reason we're doing that is because after we do the balanced equation for the double displacement reactions with precipitates, we're going to go and manipulate those and write different types of equations with that. So we're going to write something called the total ionic equation, a net ionic equation. And in order to do that, we need to understand the concept of precipitates, but also something called spectator ions, which we'll discuss in more detail after we do the examples of writing the balanced equation. For the most part, you already know how to write a balanced equation. I'm just going to briefly review it with you to make sure you understand it. So here we have a question where you write a balanced chemical equation for the reaction of copper-2 nitrate solution, that's important, with sodium hydroxide solution. Be sure to include appropriate subscripts for states. So we're going to start with our copper-2 nitrate. That's the crisscross between copper-2 plus and nitrate. So make sure you review how to write formulas for compounds. And it's aqueous because it's a solution. And it's going to react with sodium hydroxide, the crisscross between the sodium ion and hydroxide. And it's aqueous because it's a solution. We're going to write an arrow, and the Cu and the Na will switch spots. So we'll have Na go with NO3, and that will be NaNO3. Plus the Cu goes with OH. And the Cu, don't forget, was Cu2, copper-2. So it also has to be copper-2 on this side as well. And we'll have copper-2 hydroxide like this. Now remember, this is not a neutralization reaction. This does not produce one of those compounds that decomposes into water and gas or other substances. So we need to check if a precipitate will form. If they're both aqueous on the other side, if the products are both aqueous, there won't be a precipitate and there won't be a reaction. But if there is a precipitate, then we say that there was a reaction that happened. There was a precipitation reaction. So let's go look at the sodium nitrate to see what we get there. I'm just going to erase these pieces here. Sodium nitrate, and it looks like they're both soluble. So that's easy, AQ right there. Our last chance to have a reaction is for copper hydroxide. So copper-2 is over here, hydroxide's over here, wants to be insoluble at the top. That wins over the soluble at the bottom. So this here is actually our precipitate. And so we actually do have a reaction. It's our precipitate. And I put it as a solid because it's our precipitate. So that would be the solid chunks that are produced in our beaker once we mix it to solutions. So essentially, initially, you have these ions in your solution and these ions in your solution. Some copper swimming around, some nitrate swimming around. They're not really, they're separated because of the waters that surround them. Same thing with sodium and hydroxide. But once a double displacement happens, now these have come out of your solution. They're no longer dissolved in there because the attraction between the copper and the hydroxide is so strong that it prevents them from moving apart from each other, and so they're now a precipitate. And so we need to balance this equation as well because it is one of the criteria in the question. So balanced chemical equation. And so we get a 2 over here, and then a 2 over here. And I believe that is now fully balanced. We could put our 1 and 1 just as a reminder that we balance the equation. So let's try a little bit of an extension question. After you do this extension question, you'll be able to try an enrichment activity found in your slide deck. And here's the enrichment activity. It's called the Precipitation Application Jamboard. You open it up and you read the instructions, you try it out, and you can see the answers are also included there. So after doing this example, you'll be able to attempt that if you'd like. So we have a solution that has these ions in there, some lead ions dissolved in it. And that's not good. You don't want to have lead in your water. So the one strategy to remove the lead is to remove them by trapping them in a precipitate and then filtering it out. So if I produce a precipitate, I can put it through like a coffee filter or some filter paper, and then the solid will stay behind, and then the water can just go through it, and I'll remove the lead from my my solution. So you can see a demo of that over here if you want to get more of a visual, and we'll see how we can approach this. So the goal for this, the strategy is to do 2 tests. We'll do test 1. Test 1 is to take our solution, a little bit of our lead nitrate, That's aqueous. It's all dissolved in there. We don't want that. And we're going to test it with one of the solutions here because we want to see which one will remove the lead nitrate, or the lead. Not necessarily nitrate, but the lead. So let's make it react with the NaClO3. That's our first test, which is a solution. We're going to do our double displacement, and so this is lead 2, so it's going to be PbClO3 2 plus the sodium with nitrate. Sodium nitrate is NaNO3. And so what we're going to do is we're going to go take a look at the solubility of lead chlorate and sodium nitrate. Sodium nitrate, we already know from previous work that it's soluble, so that's going to be aqueous. But what we need to take a look at is our lead chlorate. Lead's over here. Where's lead? Right here. It wants to be insoluble. The chlorate's up here, wants to be soluble. So that means that compound is also soluble. So when we do this reaction, we get 2 aqueous. And so because there's 2 aqueous, no new compound is formed. The ions are still dissolved in their solution. They're swimming around together, but they haven't committed to anything else. And so there's no precipitate that forms, and you haven't trapped the lead. It's still in the water. So effectively, there's no reaction here. And so chances are you wouldn't want to use the sodium chlorate as the solution to remove lead because it doesn't produce a precipitate with lead in it. So that won't work. So we know that it's not sodium chlorate. So let's try our next test, test 2. We are going to do the same water sample because it has lead in it. And this time we're going to make it react with some NaCl, a solution of that, a few drops of NaCl. And we're going to do a double displacement, and so we'll get this sodium nitrate over here. And we know from the previous example that that's aqueous, so maybe this won't work either, but let's take a look. And then we have lead with chlorine, so that's PbCl2. And so we need to go see PbCl2 to see if it is soluble or insoluble. Lead is over here, chlorine's over here. Lead wants to be insoluble, chlorine wants to be soluble, but lead calls a shot because it's on top. And so lead chloride is going to be insoluble. It's going to be a precipitate. And so you're able to trap the lead in lead chloride. It comes out of the solution and you can filter it. So conclusion, because NaCl results in the PbCl2 precipitate, the NaCl is the solution of choice. Or you could have said the solution to use is NaCl because it results in a precipitate which can be removed, and as a result remove the lead chloride. So that was just an extension question where precipitation reactions have an interesting application. And now you're able to do the application style question found in your slide deck. So it's a great enrichment activity for you to try out. Now let's go on to the next part of our lesson, which is on net ionic equations. I'm going to briefly introduce you to net ionic equations in this video, and then in the next video we're going to do some examples together. So we have something called total ionic equations. And so I'm going to show you some images to explain those concepts. Let's go back to our little handout over here. So when we have total ionic equations, what we're interested in is seeing how the ions are interacting. And so what we do is we take our balanced equation and we convert everything into their ion form. And so this is going to be a chemical reaction where all your soluble stuff is represented as ions in their dissociated form. And that includes ionic compounds and also strong acids, and I'll show you more about that later on. But then what you can have is also something called the net ionic equation. And the net ionic equation, what that is it's an equation that shows only the ions that are really involved in the reaction, that are doing something in the reaction, and all the other ions that are not really doing anything in the reactions, we don't include them. Those ions that don't do something in the reaction, that are just kind of there, just kind of watching, they're called spectator ions. So a spectator ion is an ion in a solution that's not involved in the reaction. In fact, you could cancel them out because they're not really doing anything. So we call them spectators because they're almost like an audience. They're not really playing the sport, they're just watching the sport. And sometimes we don't want to include the audience. We just want to focus on the game. We want to focus on what's happening in the game specifically. And so the total ionic equation includes everything. It includes the audience, the spectator ions, and all the other ions. Whereas the net ionic equation says, okay, we don't really care about the audience right now, the ions that aren't involved. So let's ignore them and only include the ones that are involved. And that's a net ionic equation, the overall equation. You can think of this. So to write a total ionic equation, you need to first write a balanced equation, and then you follow a series of steps that will lead to a total ionic. And then from total ionic, you can go to net ionic by removing the spectators. So let me show you an image to highlight what that looks like. This is a chemical reaction that has happened between silver nitrate and sodium chromate, a double displacement reaction. So initially you had this solution over here, everything is nice and dissolved, aqueous, aqueous. You mix them together, and then you get this red precipitate, this silver chromate precipitate that forms, and then you still have some ions dissolved in there. Now, if you want to write a total ionic equation, what you would do is you would write anything aqueous, for the most part, to some exceptions, as their ions. So here, for example, I wrote, you'll write 2Ag plus aqueous, and then since there's a 2 in front, there's 2 nitrates minus aqueous. This is how they're actually found in the solution. They're actually found as separated ions because they're aqueous. And then for here, same idea. There's 2 sodiums, 2 Na plus, and then 1 of these chromate, 2 minus. So you need to know the charge by looking at your polyatomic ion tables. But this is how they're actually found in that solution. And then you make your arrow. And what I want you to notice is that the precipitate, you leave it as a solid because you're not separating the ions. They're not dissolved. So precipitate stays as a solid. But your other aqueous one will be dissociated into the ions in much the same way. 2 Na plus and then 2 NO3 minus AQ. And so this is a total ionic equation because it includes essentially all the ions involved, but they might not actually be involved in the reaction. So what we do is we want to figure out which ones can we remove, which ones are not really important. And so essentially you'll notice that the ones that you remove are the ones that are not in your precipitate. Really the ions that are actually reacting are the ones that form a precipitate. You have the silver and the chromate, and they make silver chromate. Everything else is a spectator. And so to write your net ionic equation, you simply remove the spectators. You can also spot spectators by just taking a look at what repeats on both sides, like 2NO3 and 2NO3 cancel out. 2Na plus and 2Na plus cancel out. These two do not repeat on both sides because you don't see Ag plus there. You see Ag in the solid, but not Ag plus. So these two are the actual ions involved, and they make this precipitate. All the other ions are spectators, and you can remove them to make your net ionic equation to really get the gist of the story, as opposed to seeing all the ions there that may not be involved. So at the end, in this little flask over here, what you have is this precipitate, and then you have these ions sort of swimming around in there, some sodium ions and some nitrate ions, but they're dissolved because they're still aqueous. And if there's any leftovers of this stuff, they might be swimming around in there too a little bit, but for the most part, you have these as precipitates. So again, this just highlights that when you're looking at everybody, the audience and the players on the field, you're looking at sort of a total ionic equation. But if you want to delete the audience and not pay attention to them and just focus on the game here, that means you're removing the spectators. You'd have a net ionic equation. And so these are the general rules for writing a total ionic equation and then a net ionic equation. Your first step is going to be to write a balanced chemical equation. After you've written your balanced chemical equation, you want to dissociate anything that's considered soluble. So anything aqueous, like ionic compounds that are aqueous, you can dissociate them. So split them into their ions. If you have ionic compounds that are insoluble, leave them as solid. Generally, molecular compounds where you see liquid or gas, they're not going to dissociate. They're going to stay as is. So H2O liquid will stay as H2O liquid. And then you have some acids called strong acids. We're going to see what strong acids are later on. But for now, I want you to memorize these 6 strong acids. This one, this one, this one, this one, this one, and this one. And that basically means that you can dissociate these. Any other acid that you see that's aqueous won't be able to be dissociated like these. So these 6 acids here can be dissociated, and these are the ways you would dissociate them. So for example, HCl becomes H plus and Cl minus, HI becomes H plus and I minus, HCl4 becomes H plus and ClO4, and then 2H plus here because there's 2 H's and 1 SO4, H plus and NO3 minus, H plus and Br minus. Notice you have to write AQ next to them and you have to put their charges. AQ with charge, AQ with charge, and that charge is from the periodic table or also from the polyatomic ion table for your polyatomic ions that you memorized back in Unit 2. So to write the total ionic equation, you include all the ions, everything that's there. But then once you want to write your net ionic, you go and you delete things that appear on both sides that aren't participating. And once those are removed, you have your net ionic equation. The only things that you really keep there on the product side would be your precipitates, things like gases as well, or liquids, because they never separated. But for the most part, we're going to be focusing on precipitation reactions where we have a solid that remains. And so we'll take a look at some examples of that in the next few slides. So essentially, these are the main steps. We're going to go over these steps together by doing some examples. You can write net ionic equations for both actually double displacement and single displacement reactions, because remember, single displacements, they will produce solids, solid metal, and an ionic compound that's soluble. And so you could actually do the same process that we're going to do for double displacements, but for single displacements. And again, as we do more practice, this will become more apparent throughout. So in the next video, we're going to go and do some sample problems of writing balanced total ionic and net ionic equations while identifying spectator ions as well.